Hi everyone, I am your host Amir Jafari, and this is the third lecture in a series of lectures on magnetic reconnection. In the last two lectures, we discussed very briefly the simplest model for magnetic reconnection, and we kind of tried to define magnetic reconnection as a rapid change in magnetic field pattern, magnetic field direction in a region of plasma. Um, and then we also estimated the reconnection speed when you have some magnetic shear in the region of plasma, say. So on one side you have magnetic field direction, for example, to the left, and then on the other hand you have magnetic field direction to the right. So it means that you have a magnetic shear, so a strong electric current there. This is the current sheet. It's called current sheet. And then uh, it turns out that plasma is kind of being pushed towards this reconnection zone by some velocity, which we want to estimate. It's called the reconnection velocity. And after pushing towards that reconnection zone, it also, because of conservation of mass, it moves out with the local Alfven speed. So to estimate this reconnection rate or reconnection velocity, you can write down, for example, the Faraday's law, the definition of electric current, relationship between electric current and magnetic field, and also use conservation of mass in a very simple way in this current sheet and get an estimate. And this simple model is called the Sweet-Parker model. We talked about this in some detail. And I also showed you that you can get the same result, the same Parker reconnection rate, using a slightly different approach, which is based on magnetic field diffusion. Uh, you basically use the Ohm's law in the Faraday's law. Faraday's law is one of the Maxwell's equations. From there, you get the induction equation, and in that induction equation, you have a resistive term, and resistive term and time evolution of magnetic field gives you an estimate about the diffusion of magnetic field in time. And the mathematics looks like exactly Fickian diffusion, what happens in a fluid when you have Fickian diffusion, for example, when you drop uh, a drop of ink in a glass of water, you see this diffusion occurs in time. It's called Fickian diffusion. And similar thing happens to magnetic field in a plasma with some resistivity. And using this approach, we got the same result. But the problem is that the Sweet-Parker rate or velocity is too slow when you compare it with the observational data, for example, from the solar wind. It turns out that you're orders of magnitude away from what we have in these astrophysical systems. In the solar corona, the same solar surface, and also in other regions, for example, in interstellar medium, etc. So, what's wrong with this model? Um, well, there is a long list of mechanisms, basically. Let's put it this way, proposed by different people in the last 6 decades, starting from 60s, basically. Uh, these are proposals to enhance the reconnection rate of the Parker model. For example, appealing, using some plasma effect, like different instabilities. For example, plasmoid instability, Hall effect, mechanisms like this to say that, well, the Sweet Parker model, in fact, uh, would give a faster rate because of these instabilities, because of these, uh, plasma effects, etc. But in this series of lectures, my aim is to show you that there is no need to these, mechanisms from plasma physics. That's not to say that these are wrong or, kind of unphysical. No, I believe that these effects can, in principle, have some effect on magnetic reconnection. And but the point is that in real systems, for example, in real astrophysical systems, for example, in the solar wind, okay, as an example, there is a phenomenon which is so efficient in enhancing the rate of reconnection that you basically don't need any of these effects from plasma physics, from small scale, uh, physics, because almost all of these proposals are based on small scale physics. For example, the Hall effect or different instabilities. If you look at, especially in astrophysics, look at any reconnection event, for example, on the solar surface, you would notice that, well, this reconnection event occurs in a flow which is not laminar, which is not in a laminar motion. It's turbulent. Okay, almost all flows in astrophysics are turbulent. What's turbulence? Well, it's a very vast and active area of research: hydrodynamic turbulence, magnetohydrodynamic turbulence, or MHD turbulence. We're not going to discuss nothing like this in this course because it's going to last forever otherwise. But we're going to borrow just one or two concepts from turbulence theory. And if you have no idea about turbulence, it's enough at this point for us here to imagine it as a super chaotic flow. For example, when you turn on your kitchen faucet, initially you have a very organized laminar flow, moving out of the faucet. But as the water velocity increases towards the ground because of gravity, at some point, if you have enough space, at some point you will notice that the flow becomes very chaotic. Okay, it's not organized, it's not laminar. Or another example, if you look at a very slowly, slow-moving creek, for example, the flow of water there is laminar, but in a waterfall, you have this chaotic, turbulent motion. And there are technicalities here. I'm not sure that we will be able to talk about these interesting phenomena in this course because we want to be very short, uh, basically number of 4 or 5 lectures here. So we're not going to have time to discuss these. But there is difference between chaos and super chaos. In turbulence, you have super chaos. It's more chaotic than chaos. But I'm going to give you some references you can find, more information on this and more research on this there. But anyway, so turbulence for us is super chaotic flow. It's non-laminar super chaotic motion. What happens in turbulence is that, as I said before, when you look at magnetic reconnection in terms of magnetic diffusion, you can imagine that magnetic field lines are kind of diffusing away, and this means that the direction of magnetic field changes over time. So this gives you the same result as, Sweet-Parker result. So you can understand, the point is that you can understand Sweet-Parker reconnection in terms of resistive diffusion, and we did this before. But the point here, when we talk about turbulence, is that, well, you are focused on a very small scale here. You're talking about resistive diffusion. It occurs on very, very small scales in the plasma, where resistivity becomes important. At much larger scales, technically these are called inertial scales in turbulence, there is a more efficient phenomenon, namely turbulence, which gives rise to a more efficient diffusion for magnetic field. That diffusion, which is called the Richardson diffusion or turbulent diffusion, is what you need to in fact, understand reconnection in real turbulent flows. So, long story short, the Sweet-Parker model gives you a very slow rate because you're comparing it to real flows where you have turbulence. In the Sweet-Parker model, there is no turbulence. It's implicitly assumed there that you have a laminar flow. But in reality, where our data come from, we have turbulence in the solar surface, for example, the solar wind. So there we have this phenomenon, this important phenomenon of turbulence. So we have to modify the Sweet-Parker model or invent another model which takes into account the role of turbulence. In this lecture, I'm going to give you some taste of this in a very simple way. And in the future lectures, we're going to refine this and kind of, make it mathematically more precise and go to some details, so on and so forth. But here, let me begin with this notion of turbulent diffusion. Initially, let's start with the hydrodynamic turbulence. So what you have in fluid mechanics, or in the simplest case where there's a magnetic field or plasma, you have just a, fluid, molecular fluid, for example, molecular liquid. You have this fact known as the Richardson diffusion, which is basically a two-particle diffusion. Okay, so you have two particles, one here, say XA, and this is XB. By X, I mean the position of particle A and position of particle B. Now you let these move in a turbulent flow, and they go, say, like this. And what is of interest here is this distance. Let's call it LT. The separation of these two particles. Richardson, 1926, was the first person who studied this in a scientific way. He was interested in the motion of particles in a volcanic ash. Suppose that you have a volcano. Let's see if I can draw something which resembles a volcano. Okay, and then you have this ash going out of this volcano. And if you look at particles here, one here A, one here B, he was interested in the time evolution of the separation. So if you average this, ensemble average this, you can get a sense of how this plume actually spreads in the space, in the three-dimensional space. So to say two-particle diffusion, because you are looking at the separation of two particles, and Richardson kind of semi-empirically discovered that L square as a function of time, when you do some ensemble average, is something like this. It grows superlinearly with time. Epsilon is some constant here. In the future, we're going to talk about this, but it's a constant. Okay, this is called Richardson law. Richardson diffusion, or Richardson law of diffusion, two-particle diffusion. Then this was Richardson, and after him, many years actually after him, there were other concepts in physics. Now we know that they are related. I'm going to talk about this. One important concept is spontaneous stochasticity, but we'll get there in due time. For now, what's important for us is just to understand this two-particle diffusion in simple hydrodynamic turbulence. That's it, okay? Now, before moving to MHD turbulence, magnetohydrodynamic turbulence. Also note, just to refresh your mind, just to remind you, that any particle here, A or B, doesn't matter, both of them, this x is basically xp, a function of time, obviously, the position of a particle. It's Newtonian physics, if you like, from some coordinate system, from some origin. And for particle A as well. And as the particle moves with some velocity, local velocity v, what you have for this trajectory in space, it's a curve in three-dimensional space, is this equation basically, which defines this curve, v, x, t, and t. So by local velocity, we mean that velocity is a function of space and time. And if you have some initial condition like this, this is an initial value problem which defines your trajectory. And this trajectory is called a Lagrangian trajectory. It's the trajectory of a fluid of parcel or a fluid particle in a space as time passes on. Okay. If you follow a particle in time and space, basically, that trajectory is called the Lagrangian trajectory, and it's defined by this differential equation. In the future, we're going to see that the behavior of this velocity field, v, mathematically, whether it is Lipschitz continuous or Holder continuous, is very important, and it gives rise to very important physical, leads to different behaviors, basically. Let's put it this way. So this is hydrodynamics, this is fluid mechanics, whatever you're familiar with this. Now let's move to MHD turbulence. And we'll see why we need this Richardson diffusion, basically. MHD, now we are talking about magnetic fields. Say you have a magnetic field in a region of plasma. You can imagine it in terms of magnetic field lines. For example, these curves, suppose that they represent magnetic field lines. And what we mean by reconnection is that all of a sudden we see that this pattern, which evolves in time, by the way, this is time, for example, t0. After a little while, if you follow these lines, they go maybe something like this. So it's t0 plus delta t. Again, if you follow these field lines, for example, for an even later time, they evolve in time. The point is that they evolve in time. But the difficulty with field lines is that you cannot, especially in turbulence, write down equations which basically describe these field lines as a function of time with preserved identity. In other words, you cannot imagine field lines like well-defined curves in three-dimensional space, which evolves and deform and evolve in time as we follow them in time, as time passes on. So they don't have identity in time. In turbulence, this becomes very tricky, actually. And even in laminar flows, if you use magnetic field lines in order to study magnetic field in reconnection problem, at least, you're going to have this problem of the relative motion or relative speed, the relative velocity between magnetic field lines and the plasma. Also source of great confusion. There are different ways of defining this velocity. So long story short, as far as reconnection is concerned, if you use this concept of magnetic field lines, well, it's going to give you some, difficulties. So I'm going to avoid this notion altogether. I'm not going to use magnetic field lines in this series of lectures, but there is an equivalent way which is much simpler. What is that? Well, imagine that you have like these two magnetic fields. This is region of plasma, okay? And better yet, let's put it this way, because we are talking about reconnection. Say there is magnetic shear in this region of plasma, and all of a sudden reconnection occurs, and what you get is something like this, right? We talked about this in the previous lectures. So this is what you get. You see that in terms of magnetic field lines, well, especially in three dimension, it's very complicated when you imagine this phenomenon in terms of these field lines, these curves. But uh, the alternative is that instead of field lines, look at uh, let's get back in this picture. Instead of field lines, focus on small disturbances in magnetic field. Okay, these are little local, like small disturbances moving with local Alfven velocity. So this is a disturbance, a wave moving with some velocity, Alfven velocity in this direction. This is moving to the left, for example. So the idea is that instead of these field lines, okay, think about these disturbances. Why? Because if reconnection is going to occur here, all of a sudden what happens? You have reconnection of field lines, so to speak. So the name reconnection. But you can imagine that when reconnection occurs, these two particles initially with this distance L0 are gonna separate very rapidly. For example, here, and this is gonna go. So the point is that because of rapid change in magnetic field pattern and direction, these disturbances will separate very suddenly from each other, and the distance between them will increase, basically. So in this picture, it's enough to look at the separation of these two disturbances and study this separation in time. Exactly like Richardson, who studied real particles in a volcanic ash. Here you say that, well, instead of real parcels of fluid, I'm looking at magnetic disturbances. Mathematically, it's the same problem. Why? Because these disturbances, these waves, have some position, and that position, for example, for this particle is given by this equation, is defined by this equation, because we say that the magnetic disturbances move with local Alfven velocity, and local Alfven velocity is basically B magnetic field at that point and time over 4 pi rho. Rho is the density of the plasma. For simplicity, I'm going to assume a incompressible flow here. So rho is density, which is rho is constant basically. So you can say that, well, dx over dt moves with velocity, which is basically magnetic field. You can absorb this density and factor of 4 pi to the definition of magnetic field. So you see that this equation here is basically the definition of Lagrangian trajectories in hydrodynamics. There we are talking about the motion of real particles, real parcels of fluid, if you like. And here we are talking about magnetic disturbances. Now, again, in the next lecture, I'm going to show you how this follows from here if there is turbulence. When there is turbulence, this velocity field V, turbulent velocity field, becomes non-Lipschitz mathematically. We're going to talk about this. If you are not familiar with this condition of Lipschitz continuity, we're going to talk about that. although it's very simple. It's a simple mathematical concept. But the point is that in turbulence, it's well known that the velocity field and magnetic field in a plasma also become non-Lipschitz, and from there you can actually deduce something like this. Okay, in the next lecture we'll see about that. And here as well, we see that, well, in turbulence, because of we have some empirical evidence, important empirical evidence, that the Alfven velocity becomes non-Lipschitz, and from this non-Lipschitz condition for VA or magnetic field, from this definition basically, um, you get L square, the distance between magnetic disturbances going as okay, exactly like the Richardson diffusion for real parcels of fluid. So the point is that because in reconnection, we can imagine that two disturbances in reconnection zone will suddenly separate from each other in a very rapid fashion. So if you look at their uh, separation, in reconnection we expect a very sudden jump in this separation, if you like. So it's useful to study that separation. And we have empirical evidence, we're going to talk about that, that in turbulence, magnetic field and velocity field both become non-Lipschitz. And from there and other, observations and experiments, we know that this is what happens. And here I'm going to use epsilon prime because this is not the same epsilon here. These are for fluids. Let's call this LB. Okay, and maybe here as well, but it doesn't matter. You get the idea. These are not related, and these constants are different. Okay, now that you have this separation, square separation, ensemble average of this square separation for disturbances. So let's see what happens in reconnection. In reconnection, say you have a current sheet of length delta. So for two disturbances, one disturbance, say, moving with Alfven velocity out of reconnection zone. So we have this kind of motion here for the plasma. How long, and this is the trajectory of that disturbance, if you like, this disturbance, okay. How long does it take for this disturbance to travel through the current sheet? Well, it's going to take T delta over VA, right? And also we have, as before in the last lecture, we have conservation of mass. So VA, from here we have VA times delta times VR. So this is VR, reconnection speed, VR. And now we have this relationship for L square. Now here's going to be delta square because the distance, the width of the current sheet is given by delta square. So this relationship here, Richardson law for magnetic disturbances will be written in terms of, its time dependence would be something like this. And what's epsilon or epsilon prime? Now we know these. The only thing that we can now borrow from magnetohydrodynamic turbulence, and I'm not going to show how it results, but we just use this fact. I guess this is a notation I usually use, right? Li. So in order to produce turbulence, what you do when you stir your coffee with some spoon, you inject energy at a large scale and that energy goes down as a cascade towards smaller and smaller scales, and at the dissipative scale, where viscosity becomes important, it is converted into heat. So when you stir your coffee, basically the length of that spoon that you are using uh, is kind of this Li here. This is the injection scale, okay? And the velocity with which you stir your coffee is injection velocity, UL to the power of 4, and VA is the Alfven velocity. So this constant epsilon prime that we're going to talk about in future lectures given by this expression. So if you plug in these relations, what you get for VR would be something like VA in my notation here, L over Li and square A, and this is basically delta, the length of the current sheet. MA is the Mach number, basically, Mach number. This is called Lazarian-Vishniac 1999 reconnection velocity. It was also recovered later by Ink in 2015, and there is another paper by all of these guys, Lazarian-Vishniac, Ink, 2015. You can look up these papers, especially this one. There we got this relation, this reconnection velocity, using this concept of Richardson diffusion, but they used this notion of Richardson diffusion of magnetic field lines. Here I didn't use field lines, I used these disturbances. Okay, Alfvenic wave packets, if you like. So you see that the point I'm trying to make in this lecture is that one, turbulence is very, very efficient, very important in reconnection events. If you compare this result in the future, we're going to do this. I mean, numerically, I'm going to give you some values. You'll see that this is in perfect agreement with observational data, for example, from solar wind, and also in good agreement with numerical simulations. One important aspect of this result is that it's totally independent of small-scale physics. There is no resistivity, for example, inside this formula for reconnection speed. It's all about the turbulence and length of the current sheet and injection velocity. So it's about local physics of turbulence, basically. No plasma effect here, which makes it kind of general because we see that reconnection is fast and is kind of ubiquitous. It occurs in almost everywhere in astrophysics, from solar wind to accretion disks. So this formula kind of shows that why this is the case and why it can be very fast, independent of small-scale physics. This is one important point I'm trying to make in this lecture. And it says that basically you don't need other effects, for example, different instabilities, Hall effects, etc., from plasma physics in order to enhance sweep Parker reconnection. Just look at the real, what you see in reality. Turbulent flows, if you take into account the role of turbulence, you see that it enhances reconnection velocity orders of magnitude, and what you get is in perfect agreement with observations and numerical simulations. And another point is that using this notion of field lines is kind of complicated and source of great confusion in reconnection community, and I think that we should drop using it. I've had long discussions with my colleagues about, for example, defining the relative speed, relative velocity between magnetic field lines and the plasma. There are different ways to do this. In turbulence, it gets more tricky. So I guess it's not I believe basically that it's an unnecessary complication. You can use these uh, magnetic disturbances or Alfvenic wave packets. I call them Alfvenic wave packets. And there is this, I've talked about this in a paper recently, which is about the turbulent topology of magnetic field, but I've discussed some details of this picture there. You can look, it's under review, but it's also available on archive. What was the title? The title was Does Magnetic Reconnection change topology? Because also there is this question um, that can we define magnetic reconnection in terms of magnetic topology change? Um, so I tried to answer this question and get some mathematical, formulation of magnetic topology change and its rate in this paper. But there I also use and explain this picture of using magnetic disturbances as particles or Lagrangian particles. Um, so in the next lecture, I'm going to give you some numerical, in fact, values based on this formula and its, a comparison with what we have from observational data and numerical simulations also, and a couple of references about this. And then, more importantly, we're going to discuss this Richardson law, especially for magnetic diffusion in some mathematical detail, why we have this, and also this Richardson diffusion. So this is called Richardson diffusion. Richardson himself, of course, didn't talk about magnetic fields. He, let's see, because here you don't see all my Richardson. My whole screen is not shown here for some reason. I don't know why. So Richardson diffusion is also related to Kolmogorov. Kolmogorov 1941 paper about turbulence. We're going to talk about these, and also these are related to a phenomenon called spontaneous stochasticity, which is kind of super chaos. If you are familiar with chaos theory and butterfly effect, this is related to that effect. So these are important concepts, for example, the spontaneous stochasticity, which follows from the Richardson diffusion, basically, very naturally. You basically give up classical determinism. You know what this? There have been this discussion in the last, I don't know, the whole century, basically, in the 20th century and up to now, that this the breakdown of determinism in quantum mechanics has been source of these discussions, saying, for example, asking questions like the human brain, human mind, is it quantum mechanical system or is it a classical system? Does this notion of free will come from quantum mechanics because of Heisenberg's uncertainty principle or not? But so these are probably familiar questions to you too. But it turns out that in classical physics, we have indeterminism as well. In the spontaneous stochasticity, as we will see, which is related to reconnection, but in a more general context. In spontaneous stochasticity or super chaos, the system forgets its initial conditions, and no matter what kind of initial conditions you feed into your system, you're going to get a different, independent kind of final result, which is kind of weird in classical physics, but it seems to be um, what happens in nature, and it's related to this concept of this phenomenon of turbulent recognition. So we're going to talk about them, but in the next lecture, I'm going to repeat these concepts in a more, mathematical way, kind of more mathematical way. We're not going to be very mathematical at any, uh, on any scale of in these lectures. But this Richardson diffusion deserves a kind of more detailed discussion, especially the lack of Lipschitz continuity of magnetic and velocity fields in turbulence and its relationship to Kolmogorov theory. These are important to discuss, and they are related to anomalous dissipation. All these should be basically kind of covered in one or two lectures. But let's see how we proceed after discussing the more mathematical form of the Richardson diffusion.